All right, ladies and gentlemen, welcome back to another round of chemistry information. This is Mr. Doolin. Thank you so much for tuning in for this. Today we're going to take a look at photoelectron spectroscopy. We've been looking at ionization energies, we've been looking at electron configurations, and da-da-da-da. We've been talking about where these electrons are at. And so now what we're going to do is we're going to take a look at how do we really know where those electrons are at, right? And that's what photoelectron spectroscopy is going to do for us. It's going to allow us to look at some data and look at energies of electrons and actually interpret some of this to say, oh, that's why electron configuration is like that. That's why those are there, all right? Okay. So what I've got drawn here is I've actually got Bohr's model of a sodium atom written there. I want to remind you of a term I hope you know called ionization energy. Right? Remember, ionization energy is the energy required to remove an electron. And so with sodium, I want you to understand that we actually have ionization energy number 1, we have ionization energy number 2, we have ionization energy number 3, so on and so forth, all the way to the point where we have ionization energy number 11, because sodium has 11 electrons, right? It has 11 electrons when it's a neutral atom. So, how are we going to do this, and what does ionization energy actually look like? And so what we do is we take energy, right? We'll take energy. That's an ugly looking arrow right there, but it is what it is. So we can take this energy, and we're going to shoot this energy at the atom. And what the atom's going to do is if it actually hits an electron, if it has enough energy, it will eject the electron, if I remember how to spell here, it'll eject this electron out of the atom, right? And that's what ionization energy is. Now, if we go back and again bring in somebody's law that we know, this force of attraction, Coulomb's law, we understand that this distance part of the equation makes a difference, and the closer that we get into the nucleus, the more energy that we would actually have to put in. So if I'm going to go through all 11 ionization energies, I expect the valence electrons here to be the first electron to, if I put enough energy in to take all of them off, I expect the valence electron energy, or the valence electrons, to come off first, and then successive ionizations to occur after that, all right? And so the big thing that I want to take away from this, and I want you to remember, is that the closer to the nucleus equals more energy required to remove the electron. So the closer to the nucleus, the more energy is required to required to remove the electron, and that should make sense based on Coulomb's law, right? All right, and so what I've done is I've just erased that there, and you can just keep on going, but now we want to take a look at two different questions here. Number one, how do we know all of these energies? Like ionization energies, yeah, they're just numbers in a table to you most of the time, but how do we actually know them, and how do we know what they are? And then number two, how do we know electron configuration is a real thing? Like, Mr. Doolin, why is that electron in that first energy level? What does that actually mean? Why is it different than the electron that's in the third energy level? And how do we know that? All right, and so what we do is we bring in photoelectron spectroscopy. And so I'm going to start drawing here, and then I'm going to finish drawing it. I'm going to pause, and I'm going to finish drawing here. Okay, and so I finished drawing here, and just take a second, and you can draw this as you listen to me. But essentially, what we've got is we've got an energy source over here. This represents over here our energy source. Now, notice from the electromagnetic spectrum, remember that X-ray is a very, very high energy photon, and so what we're going to do is to get those core electrons, those inner electrons, right close to the nucleus, we're going to have to put in a lot of energy. And so we're in this part of the electromagnetic spectrum when we're trying to get down to the resolution of those core electrons. And so what happens is we get this, and it shoots this energy, right, an energy beam, and what happens is an electron will actually be knocked off, right? And so we know exactly how much energy we're putting in. An electron will come off, and then what happens is it comes through this tube, and just like mass spectrometry, where we have a magnetic field applied to this negative charge, we can actually detect how many they're showing up. And not only that, but we can figure out how fast this sucker's going, because when it comes off of the substance, it actually has a very specific kinetic energy. And remember, kinetic energy is this energy of motion. And so it's really important to understand that as we knock these electrons off, they're coming off with a certain amount of kinetic energy. And so a couple of things that we know. We know our energy input. We know how much energy we put in because we actually dialed up our energy source and did that. The next thing that we know is law of conservation of energy says that we have our kinetic energy of our electrons, and then the difference between those two things here is what we're going to call the binding energy of electrons. And this is what we actually want. This is what we want. This is the energy associated with that electron, right? Because what we do is we take this kinetic energy of the molecule, is we measure this, right? We use the detector to measure, because just like anything else, the speed of this molecule, or this electron, sorry, I was thinking isotopes, the speed of this electron determines if it makes it through. If it hits up here, right, that means it's going faster than if it hit down here, right? So these are going to be our slower, these are going to be our faster, and when we get it to hit to the detector, we can actually determine, hey, that was the kinetic energy of that, because now we're not talking about different masses. They're all electrons. It's an electron. It has the same mass. It has the same charge, and so we can dial up this this magnetic field and actually determine how fast it's going. All right. And so what we do is we measure the kinetic energy. We know our energy input, and what that tells us is the binding energy of our electrons, and that's the energy of this electron. Okay. And so now we're going to get into what does this actually look like? What does the data look like? Okay, and so now what we've got here is we've got a graph. Notice the axes on these. I've got number of electrons over here on the y-axis, and then I've got my binding energy on the x-axis. Notice the largest binding energy is over here in the left-hand corner. This graph, the axis here, is backwards from what you're normally used to, and you can think of the nucleus as being right there, right? That's my nucleus. The closer I get to that, the more energy it is an easy way to remember this. But always double check your axes there, all right? And so what we would see, if we were actually looking at a sample of boron, we know boron's electron configuration to be 1s2, 2s2, 2p1. So what would the readout, the photoelectron spectroscopy readout of boron look like? And what we would end up is this, is we'd have a peak about right there. We'd have another peak right over here at about the same height, and then we would have a smaller one that's about half of that peak height right there. So we would get three different readouts. Now notice on the electron configuration, I technically have three different kinds of electrons, right? I have three different energy electrons, and that would make sense. We would expect the 1s electron to actually be the closest to the nucleus. It would require the most energy to actually remove. And so notice the height of the peak here, right? That's an important thing to understand. The height of the peak, and we know this is 1s, it represents 2 electrons. So I would expect over here, right, my next one would be my 2s peak. I would expect it to be the same height as 1s if it was 2 electrons, and that is what we see. And then this last one here, this is my 2p1. All right? And so notice as I get further away from the nucleus, my binding energy goes down, right? And then the size of the peak, the height of the peak, is indicative of the number of electrons. And so that's a couple of things that I definitely want to make sure, right, is I need you to understand peak height, right? That's actually indicative of the number of electrons. And then I want you to understand what it means if you have higher binding. Let me get this word down here, binding. If you have higher binding energy. Like, what does that mean, right? And that actually means it's closer to the nucleus. And so we can interpret the photoelectron spectroscopy readout, and we can actually determine and infer what the electron configuration is. Where are these electrons? Like, what then use? I mean, it's all based on Coulomb's law, right? That distance is proportional, or inversely proportional to that force of attraction, all right, and how much energy it required to remove those electrons, okay? All right, so that's it. There was a lot here, ladies and gentlemen, to squeeze into 10 minutes. Make sure you get your questions down. We will address those in class. We'll do some practice with determining this. We'll see some videos and some animations for this in action, and hopefully that will clear anything up if you're still unsure about that. Otherwise, I will see you in tutorials, and thank you for tuning in.